Hello guys, you know what's funny is I actually might be a floating head again, so I might just keep my green screen background because I realize I'm wearing black. So when I get rid of the background, I actually might be a floating head again, but I'm not changing. Anyway, what we have here is I want to talk about different circuit types. So on part 3 of that worksheet or the FET experiment, I wanted you to look for trends, that when you had something in parallel and series, what happens to voltage, what happens to current, and things like that. So we're going to try to talk about the two main things today, which is series and parallel. And the reason why I have Christmas trees up here is that Christmas trees are the best example of this. So, if you were a kid, or actually you guys, put up your Christmas tree lights and stuff. And what in my past, most of our lights were in series just because it was cheaper. So when one went out, the whole string went out, and you're just going through each one trying to figure out which one's the wrong one, and it could take like easily 30 minutes to an hour, depending how long that string is. You have to pull out each light bulb out, plug it back in, or you're just looking at it. Nowadays, you have parallel circuits where if one goes out, the rest of them are still there, so we're okay. In our house, it's actually a combination of both series and parallel. Real life, you take advantage of both pros and cons of each circuit, and we'll kind of talk about that and introduce other properties that you might see in the house because of the pros and cons of series and parallel. Anyway, series. If you haven't noticed already, this is the best answer that I can. I just Googled it, and this is the perfect one. And the reason why it's perfect is because that's right here. It only has one pathway. That's the most important thing right there. So when you look at here, the long one's plus, negative. As the electrons are going, actually electrons are going the other way, but let's just say we're going in the same direction as currents. As the current is moving that way, the electrons, I guess I'll write it this way, only have one pathway. They don't have another pathway to take, so they're forced to go through all three obstacles. So this is the drawing for a resistor. Almost everything that you plug in is considered a resistor. And if you remember back, I think 2 days ago, I asked you to define what a resistor is, or at least in your thing you were defining what a resistor is anything that impedes the flow of electrons, so it slows it down. So when you plug in a light bulb, it slows down the electrons in it, so it's going to be harder for it to go through. It's a resistor. If you plug in your refrigerator, same thing. If you plug in your phone, same thing. All these things are making it difficult or making the electrons or current do work, and that's what we want. If there's no work done, which was the short circuit, we're not getting anything out of it. So we want to make sure that we're making it do work, and resistors do that. Now, if we look at a parallel, let me change it back to cursor. If we look at a parallel, oh man, did I pull the same picture? Okay, give me a second, let me fix it. All right, so I fixed it. Apologize. I didn't realize I pulled the same picture. But anyway, here's a parallel. And what's nice about this parallel one is that let's say the electrons is still moving this way. So I know current goes this way, but I'm going to follow electrons. Electrons go the opposite direction. So the electrons could come here, and right here it has a choice. It could either go straight or this way. So let's say a blue electron goes this way, and the rest of the pink ones are still going this way. So one goes off, another one goes here, and here you have another choice, this way or this way. So let's say a yellow one goes over here, and then the pink one keeps going on and on and on, and I'll kind of redo it so that it makes more sense. Here's the blue one, here's the yellow one, and then finally the pink one chooses to go this way. So the electrons have a choice between 3 different pathways. In this case, it could be just 2. In this case, there's 3 different pathways they could go through, and it only has to go through one. Electrons are always, their goal is to go from negative to positive. So once it's here, there's no reason for it to turn back this way. Its goal is to get to the positive, so it's going to go this way. So one pathway is this one. Another pathway is this one. And the last pathway is this one. So each of these pathways, the electron only encounters one resistor or one load that it has to go through. So the cool thing about this is that if the pathway is broken, let's say something happened to this. This pathway got messed up. The light bulb went out, whatever. We still have two pathways for the electrons to flow, so the circuit still works. When you look at the other one, this one, if one of them is messed up and the circuit is broken, the electrons are stuck right there and then it stops flowing. So when it's a Christmas lights in a series, if one light bulb goes out, that filament is broken, so electrons can't pass through that filament anymore, then what's going to happen is that current is broken. So hopefully you kind of saw that in the FETs that we have. So here we have the FET. I already created two circuits. This one's in series because you have one pathway. Electrons have to go through all three light bulbs. This one you have three choices, and I can make this even more obvious. So what I like is if I broke this up and if I do it this way, it will make it more obvious that the electrons have more than one choice. If I pull the wire out here and then reconnect it right here, it's the same exact thing. You'll notice that once I connect it, it'll look exactly the same. But when we look here, the electrons have a choice. 1, 2, 3. Since these are the same light bulbs, each one of these are 10 ohms, they're equally the same, meaning that this pathway is just as hard as this pathway, so they're going to split evenly. So if we look at an ammeter, oh, I have to hook it up. I wonder if there's a cheap way of doing that. Let's see. I guess not. I guess I have to look. But if you look at it, let's see. Values. There we go. If we look at the values, let's see, does it show me the current value? It does not show me the current. Why can't it just show me? Okay. Doesn't. Okay. Anyway, I guess I could attach it, but I'm too lazy. Let's see. Break. They're all going to be the same. I'm just going to give you that. So if this is If this is 2.7, then each of these are 0.9. It's going to evenly split between the two. When you look here, electrons all have to go through all three, so what's going to happen is it's going to slow it down. And that's the pros and cons of these circuits when we have here. So for series, the pros, it's easy to make. Look how much little wire I have compared to this one. Okay, it's easy to make. The current is the same throughout the whole thing, so it's easy to calculate. It's easy to make sure that you're not going to blow anything up. And the two main things is that we have in our house is that it doesn't overheat easily, and that's a main safety thing for our house. We want to make sure that we don't have fires in our house, because I remember back in our previous lecture I said that if we overheat the wires, it's going to cause fire or short it out. You could do that with a parallel. If you plug in more and more stuff, the current's going to get faster and faster. So let me kind of show you. So I'm going to break this one and watch what happens to the current. It's going to slow down. I'm going to break this one. Slow down. So when you have more things attached, the current goes faster, which kind of doesn't make sense until you think about it. What I'm doing is adding pathways for the electrons to move through. So just think of a door. So if you had a door in one room, and that door could fit one person a second, that's good. Now, if you put another door in and it's still 1.1 person per second, all of a sudden more people could exit the room. If I have 5 doors, then 5 people could exit the room faster. Every time you add a door, more people get out. So every time you plug in something, there's more pathways for the electrons to flow, so that means the current's going to go bigger. Now, that's kind of the dangers of plugging too much things in one socket, is because all of a sudden you're drawing a lot of current from that just one socket, which might overheat, blow up, things like that. So that's why you don't want to plug in everything in just one socket with a power strip. You kind of want to spread it around in different outlets. So pros is that it doesn't overheat. You can increase voltage, which we'll show later. And the current's the same, it's easy to make. Now the cons are kind of what it is. If one breaks, the entire circuit breaks, and as the number of components increase, the greater resistance. So what's going to happen is, if in this case, you'll notice that if I add more light bulbs, the brightness still stays the same, no matter what, for each one. And that's an advantage. But for series, if I add another light bulb, it'll get dimmer and dimmer. So here's that one. So before it was, now it's barely lit, but if I just only had one light bulb, you'll notice that it's much brighter. And let me just cut this one so it's more obvious. Okay, so this one's much brighter, but if I connect them all and break this one, they're much dimmer. So that's kind of the disadvantages. The advantages, once again, it's that it's easier. You can increase voltage. Current's the same throughout the entire circuit, easy to make, but it's, if one breaks, the entire circuit fails. And if if you add more stuff, then it's just not practical. So that's why we have parallel circuits. The pros: voltage is the same throughout the whole thing, because each one is directly connected to the battery. So the electrons are only going through one resistor. So that means it's going to experience the same voltage on the battery, where this one, the electrons are going through three things. So this one waterfall has to go through three obstacles, where the other one is, it's one waterfall, only picks one of the objects. So the energy is still there. Current is dependent on the load. So, it's dependent on how much resistance it is. If I increase the resistance here, the current will be slower in this pathway. If I decrease it, it'll be faster in that pathway. So you kind of see what happens if I decrease it. So it's dependent on that load or that resistor. One doesn't affect another. So if I increase this, the other ones are still the same. The only way it'll ever change is if I short it out. So here's the shorted out. Short means there's no resistance, so there's no reason for electrons to follow the other pathways. But once you introduce any kind of resistance to it, it gets back to normal. And if I disconnect one, the others still work. So parallel is really advantage, but the disadvantage is really dangerous. It's more complicated. You can increase voltage, and the main thing that we want to be careful is that it can overheat. So in real life, we have a combination of both series and parallel. We try to take advantage of the series things and the parallel things all at once. So parts of your house are in series. So you have a circuit breaker which is in series with your circuits. Your outlets are parallel because you don't want to turn on all your lights to have all the lights on. I mean, it would suck if you only have, it's either all on or off. So that's the advantage of parallel. You can have one stuff on and some stuff off. But at the same time, you want something in series to kind of control the circuit itself. So if you overload a circuit, the circuit breaker will break, save your house from catching on fire, but then you have to go outside and turn it back on. And we'll talk about that a little bit later once we kind of go over the pros and cons, or the equations of circuits. So why here is the circuits. I found a really cool website that you guys could kind of go through, and then we'll do some problems together. We'll see how it is. It is online, so it's going to be more difficult. To be less, I think I'm going to focus more on properties, but I do want to get some practice in. So this website does a really good job breaking it down, very simplified, and then we'll kind of go through it together, probably just on the tablet, writing through it. But you'll notice for series, you have a set of rules here. For parallel, you have a set of rules here, and we'll kind of go through these. So spend the next few days kind of going through these, but I do want you to go through the website first because he does a really good job, or she does a really good job explaining that stuff. So hang in there. Best of luck. I'll probably get this up on Thursday. We'll see how it goes, and we'll get some practice problems in. All right. When it talks about grades, I think you guys all heard is pass, no pass, or credit, no credit. You do get to opt in to have grades. I'll be honest, most likely everybody's going to get an A unless you do absolutely nothing. So for our physics honors, I just suggest that you request for a grade. I will have your final grades pretty much done by the cutoff date. So I believe you get till June 6th to decide whether or not you want it or not. I'll have your grades pretty much done by June 1st, so you can see what it is and you can decide for yourself if it's something you want to keep or not. It never hurts you even if you get a B, but obviously it's nice to have that in your notes section. But it is only in the notes section. It does not help your GPA at all. So that's why there's no reason for me to be picky about it, because it's a crappy time. So let's just get through it. I'm kind of more upbeat because it seems like we get to reopen soon. Maybe we even get to start early August. We'll see. I'm getting tired of staring at the screen, and I'll be really excited to see you guys again. All right, so take care, and I'll see you guys soon.